Welcome to This Explainer. Today, we're unpacking something genuinely groundbreaking in the math world that fundamentally changes how we translate polynomials into matrices. If you've spent any time in algebra, you know that nonlinear equations and linear systems usually feel like entirely different universes. But what if we could just bridge them, reversibly? Well, today we're exploring the work of Morad Sultan Ezouidi, who has mapped out exactly that. So, here's the crux of the whole problem. For centuries, literally centuries, mathematicians have just hit a brick wall trying to find the power sums of a polynomial's roots. Historically, to understand the deeper structure of a polynomial, you basically had to find its roots first. And let's be real, finding roots, especially for higher degree polynomials, is incredibly complex, sometimes even impossible. So the million-dollar question is, what if there's a direct, elegant shortcut? What if you could build a linear system without ever needing to know those roots at all? And that brings us to this ancient friction point. Classical methods completely box you in, forcing you into this messy process of solving for the roots first, just to calculate things like power sums. The new Ezouidi method, however, bypasses those roots entirely. By working straight from the polynomial's given coefficients, rather than fighting to find the roots, it completely sidesteps the traditional, painful route. I mean, it's a total paradigm shift for algebraic problem solving.
All right, here's our blueprint for crossing this bridge together. 1. The math connection problem. 2. The Ezouidi substitution. 3. The second theorem. 4. Building the matrix. 5. A concrete example. And 6. The complete duality. Starting with section 1. The math connection problem, islands of algebra.
Now, take a look at our master map here. This is Morad Sultan Ezouidi's triple duality schematic, essentially acting as a mathematical Rosetta Stone. Like we said, polynomials and linear matrices have historically felt like isolated islands. Sure, classical frameworks existed, but none of them directly transformed a univariate polynomial into an equivalent linear matrices system. The bridge simply didn't exist. But looking at this schematic, we finally have a continuous, flowing loop. You start with an alternating sign polynomial on the left, hit it with the Ezouidi substitution to flatten it into a homogeneous linear equation in the middle, and boom, you build a highly structured Ezouidi matrix right there on the right. And since it's a duality, you can run the exact same process in reverse. Moving right along to section 2, the Ezouidi substitution, the first tool. So if we're going to transition from a curve to a grid, we need a mechanism to swap out those pesky nonlinear elements. Enter the Ezouidi substitution. This acts as a super clever swap, trading our standard nonlinear polynomial terms for new variables combined with the power sums of the roots. Specifically, it swaps out the traditional powers of x for an expression featuring a brand new linear unknown divided by our degree n plus a term representing the power sum of the roots. At first glance, you might think, wait, aren't we just making this more complicated by adding variables? But actually, scratch that. This substitution is setting the perfect stage for a massive algebraic cancellation. Which leads us perfectly into section 3, the second theorem, canceling the nonlinear. To make this clever swap actually do its job, we need a way to find those power sums directly without solving for the roots. That's where the Ezouidi second theorem comes in. Honestly, this is the engine driving the entire duality. The absolutely crucial part here is that this theorem lets those messy nonlinear terms just completely cancel out. It mathematically proves that an alternating sum of the polynomial's coefficients, multiplied by the power sums, will always equal 0. So when we apply this identity to our substitution, all those complex power sums just vanish. Poof, 0. You're left with a pristine, beautiful linear equation where the coefficients are exactly the ones from your original polynomial. All right, section 4, building the matrix, the structural destination. Now that our linear equation is cleanly derived, meaning we've successfully flattened the polynomial, we need to give it structure. Let's look at how we build a highly organized n by n matrix straight from these equations. It's a simple 3-step process. Step 1, we grab our newly derived linear equation. Step 2, we defined matrix entries by taking n times the root raised to a power and subtracting the corresponding power sum. And step 3, we compile those entries into a square matrix that perfectly matches the degree of our polynomial. And this resulting matrix, it is definitely not just a random grid of numbers. It has some really incredible quirks. For starters, because of how it's built, the columns of this matrix will always sum to strictly 0, no exceptions. And because they sum to 0, they're linearly dependent, which guarantees the matrix is singular. Essentially, its determinant is 0, meaning it contains overlapping information. Even cooler, if you take the alternating coefficients of your original polynomial and turn them into a vector, that vector perfectly maps out the null space of the matrix. Multiply the matrix by this vector, and it collapses perfectly to 0. Every single piece of the polynomial's DNA is right there, encoded into this singular matrix. Let's make this tangible in section 5, a concrete example, crossing the grid for n equals 2. You know, abstract math always clicks better with concrete anchors, so let's actually cross this bridge using a basic degree 2 polynomial, just to see the magic happen with real numbers. We're going to feed this exact equation, x squared minus 4x plus 3 equals 0, straight into the Ezouidi method. Here our degree, n is 2, the first coefficient is 4, and the second is 3. Now, if you're up to speed on your algebra, you probably instantly know the roots here are 1 and 3. But let's pretend we have no idea. We're going to rely entirely on those coefficients. And this is where you really see the magic trick. The Ezouidi method uses only the coefficients 4 and 3 to effortlessly hit the exact same power sum of 10. Check out the classical row. You'd need the roots 1 and 3, square them, add them up, and you get 10. But look at the Ezouidi row right below it. By leveraging the second theorem, we just take our coefficient of 4, square it to get 16, and subtract 2 times our other coefficient of 3. 16 minus 6 equals 10. We got the exact same result, the sum of the squares, without ever once touching the roots. So we plug that power sum into our substitution, and it spits out this beautifully simple linear equation, totally stripped of its old nonlinear baggage. Remember, our original was x squared minus 4x plus 3. The new linear equation is x sub 2 minus 4 times x sub 1 equals 0. Notice how that coefficient of 4 survived the transition flawlessly, but the nonlinear powers are just gone, completely replaced by linear variables. And right from that linear equation, we derive our 2 by 2 matrix. Look at those columns. They perfectly sum to 0, exactly like we said they would. Column 1 is negative 8 over positive 8. Column 2 is negative 2 over positive 2. They cancel each other out completely. And if you multiply this matrix by a vector made of our polynomial coefficients, the 1 and negative 4, it equals 0, proving the vector is in the null space. The math checks out flawlessly. Finally, section 6. The complete duality reversing the journey. Because any well-engineered bridge has to carry traffic in both directions, right? It's one thing to break a polynomial down into a matrix. It's a whole other ballgame to build it back up. But if you start with a singular matrix and its null space vector, you can just run the inverse substitution to perfectly reconstruct the original polynomial. You simply apply the inverse of the Ezouidi substitution to the matrix equations. The second theorem kicks in again, evaluating the power sums and organizing the variables step by step until, bam, you're looking right back at your original nonlinear polynomial equation. Glancing back at our master schematic, we have definitively proven that this method translates completely fluently between the nonlinear and linear realms. Those arrows point both ways for a reason. Polynomial to linear equation to matrix, and matrix back to linear equation to polynomial. It's a closed, absolutely perfect loop of algebraic logic. But here's the thing, this isn't just some elegant proof to admire on a chalkboard, it's a brand new structural tool. The only question left is, what kind of complex systems are we going to build with it next? Polynomials are foundational to so much of our world, from the signal processing algorithms running our smartphones to the cryptographic keys securing our data. Having a new way to instantly translate them into singular matrices opens up an entirely new frontier in applied mathematics. So what barriers in your own field could be broken by simply bypassing the need to find the roots? Thanks for joining me for this explainer, and keep exploring.